it never hurts to hear these things twice. So also, I'd like to acknowledge my collaborators on the last bit of the talk, if I get that far. So this was work done with Jean-Louis Gibaudot and Fausto Catania. Fausto gave such a nice talk last week. And a postdoc, or an ex-postdoc of mine, Pallavi Bhatt, who's now at ICTS in India. She has a permanent position there. Some of the things I'm going to talk about are in a recent perspective that I wrote, Fluid Dynamics perspective, Journal of Fluid Mechanics perspective on the turbulent dynamo. This is open access at the moment, so it's a good time to download it. But there's also some very nice recent reviews I should advertise. There's obviously the book by Keith Moffat and Emmanuel Dormy, which is incredibly nice to read. And there's a review by Francois Rancon, which has some very nice stuff as well, but also talks about plasma dynamos. So for those of you who are interested in plasma dynamos, that's a nice review. I'm not going to talk about plasma dynamos at all. Okay, so I'm going to give a brief introduction at the start. So I'm going to talk a little bit about the Earth's magnetic field and the problems that we have in dynamo theory to do with geomagnetic field generation, but mainly I'm going to talk about the sun's magnetic field and the field of galaxies. And all I'm hoping to get across there is that these two problems are difficult for different reasons, okay? And I'll try and explain the reasons why they're difficult. And there's no one size fits all for dynamo theory. So here we have a nice picture of the Earth's dynamo. The Earth's dynamo is believed to be generated in the fluid outer core, as Fausto said. And because of the interaction of rotation and convection, you tend to get the alignment of the fluid convective flows with the rotation axis. And it's an interesting question as to how these can generate some magnetic field. Here we have the, if you like, the paleomagnetic history of the Earth's magnetic field. So black is field of one polarity, white the other, and we can see the Earth's magnetic field flips irregularly on a long time scale, certainly a long time scale compared with the flipping of the sun's magnetic field, as we'll see. And it's interesting that it flips rarely. So it might be possible to use rare event theory or some algorithms from rare event theory to try and understand what's going on in the geodynamo. But I'm not going to talk about that today, but it's an interesting thing to think about. The sun's magnetic field is rather different. Let's see if I can play this movie. So this is a magnetogram of the magnetic field at the surface of the sun. So yellow is field of one polarity poking out the sun. Blue is magnetic field of the other polarity. And what we're going to be able to see is that magnetic field comes and goes. I'll play this movie a couple of times. And waves of magnetic activity migrate from mid-latitudes to the equator. What you might be able to see possibly just at the end of this movie is that in the northern hemisphere, you have a sunspot pair with a certain polarity. So here, yellow is leading blue, whereas in the southern hemisphere, this is probably not the best choice, but here blue is leading yellow. So the field is of opposite polarities in each hemisphere. Let me play that movie again. What is quite hard to pick out is that you can see the waves of magnetic activity moving from mid-latitudes to the equator and dying and then coming back again. It's quite hard to pick out, but the polarity of the sun's magnetic field is changing. It's changing every 11 years, giving us a 22-year magnetic cycle. Okay, this is the spatiotemporal plot. It's called the butterfly diagram of magnetic field or activity at the surface of the sun. And you can clearly see this spatiotemporal order, these waves of magnetic activity going from mid-latitudes to the equator. The cycle dies out and then another wave of activity starts. And what you can see from this is that these butterfly wings, if you like, are largely symmetric about the equator. And the sun's magnetic field, when it's working normally like this, is primarily dipolar, although of course there are higher order multipoles involved. And this can be seen if we look at the next slide. If we have a look at the history of the sun, so you average over latitude and you just get the solar activity as a function of time, we have this 11-year solar activity cycle, and it's modulated on a longer time scale. And indeed, there are periods such as the Maunder minimum where solar magnetic activity, well, it wasn't visible at the solar surface, at least in the form of sunspots, although there is some evidence to say that solar activity did carry on. There was some cyclic activity, and that's known from proxy data such as beryllium-10. Interestingly, when the sun emerged from the Maunder minimum, the sun's magnetic field was not symmetric. It wasn't dipolar. In fact, the contribution, it seems like the contribution from the dipole and the quadrupole were about the same order. So this modulation affects the dipole component, or it affects all components. But when the dipole component becomes small, you start to see the higher order components. Okay. Now this is time dynamics on a time scale of about of 11 years, 9 to 11 years, and the ohmic decay time of the sun is very long, much longer than that, and so it's about the age of the sun. And so what we have here is spatiotemporal order or behavior emerging from a turbulent flow on a time scale that is different from the ohmic time scale of the sun. And so this is the kind of activity that we would like a dynamo theory to try and explain. Okay, so let's go to a bit of theory. Okay, so dynamos, in the simplest form, they involve the self-consistent solution of the induction equation and the momentum equation of MHD. So we have the momentum equation. So just so we're all fixed in terms of ideas, we're going to be doing this for a rotating system. I haven't put rotation in there, but obviously most astrophysical objects are rotating. So we could have a Coriolis force in there as well. And obviously that's going to prove to be very important. So we have our momentum equation with the Lorentz force and whatever other forces we might be interested in. Could be a buoyancy force in there. And we have the induction equation. And we're thinking in terms of the sun for a collisional plasma, or in terms of the Earth's interior as a liquid metal. And so using the induction equations of MHD is a fine thing to do. Okay. And I'd like to stress, at least here, that the theoretical and computational difficulty involved in solving those coupled equations, I believe, arises in two different places, depending on whether you're looking at the geodynamo or the solar or stellar dynamos. And this was very well put at a conference, gosh, I guess about 10 years ago, or maybe even longer, 15 years ago. Chris Jones put it very appositely to when he was explaining to a research student. And he was talking as a geodynamo theorist. He said, look, all our problems are related to solving the momentum equation for a rapid rotator. Then he pointed at the people trying to do solar dynamo theory. He said, those guys are still having problems solving the induction equation, which I think is a very apt way of putting it. We're still, most of the problems for astrophysical dynamos, if you like, arise from solving the induction equation in extreme parameter regimes. Whereas I think it's fair to say the geophysicists have nailed solving the induction equation because that's not really in a very extreme parameter regime. The problem there is all to do with solving the momentum equation. Okay. So just to fix ideas, we've got these two equations, the momentum and the induction equation. And just to say, a dynamo solution is one where the field remains finite for large times. And it's often, the dynamo problem is often split into two problems, usually in two different ways. And so historically, one often split the dynamo problem into the problem of, can a velocity field be found for which B grows? So I just choose U, I solve the induction equation, and can I find a velocity for which B grows? Now this is a linear problem in B, and so solutions will grow exponentially. And so that's called the kinematic dynamo problem. And then there's a question is, imagine I can find a U for which the field grows, and now we can find all sorts of examples of U, which leads to the growth, then how does the magnetic field interact in the momentum equation? And as Fausto said last week for the geodynamo problem, it's like, where does it enter into the balance in the momentum equation? That's a key problem as well. Okay, once you've split it that way, there is another way of splitting it two ways. And you could say, can the velocity field generate a magnetic field on a similar scale to the velocity? Or can it generate a large scale field, which is a system similar to the size of the object? So much larger than, say, a correlation length scale in the velocity. And so it might be that you can find certain examples of velocity fields which are very, very good at putting energy into very small scale magnetic fields, but they're not necessarily going to lead to the systematic behavior that we saw, say, for the solar dynamo. So this talk is mainly about the solar dynamo, but I'm just going to say a couple more words about the geodynamo. So let me say why the geodynamo problem is hard. So Fausto mentioned this again last week. There is a large separation in the timescales between the different processes in the geodynamo, and there's a very nice review by Henri Claude, who's in the audience, and Nat Schaefer, talking about the timescales and balances that are important in the geodynamo. But the timescales vary from obviously the rotation period, which is about a day, all the way up to a thermal or viscous diffusion time, which is of the order of 10 to the 9 years. The magnetic diffusion time is smaller than a thermal diffusion time. It's about 10 to the 4 or 10 to the 5 years. And the convective time, as Fausto said last week, is about 100 years or so. And so this leads to, well, very many non-dimensional parameters, usually all of which are very big or very small, depending on how you frame them. So the Rossby number here, which is a measure of the rotation period to a convective period, is very small. It's about 10 to the minus 5. The magnetic Reynolds number is not, it's not astrophysically huge. It's quite big. It's probably of the order of 500 or 1,000. The magnetic Prandtl number, which is a ratio of these two diffusivities, is very small. So there's a very interesting question about how do dynamos operate in the low magnetic Prandtl number regime. So that's a very small parameter. And then there are these other parameters such as the Reynolds number or the Peclet number and the Ekman number, which you can get by essentially, multiplying together some of these other numbers. And of course, the Ekman number is the ratio of these of the ones at either end, and that is something like 10 to the minus 15 for the Earth. So the ratio of a rotation period to a thermal or viscous, actually a viscous diffusion time, is of about the order of 10 to the 15, the ratio. There are other timescales associated with waves and other processes, and they can take anything between a few to a few hundred years. Okay, so the fact that you have this separation of timescales means that you might be able to do some asymptotic methods and naturally make use of the fact that there is this separation of timescales to derive some equations that use the ratio of the timescales as a small parameter. So I'm not going to say too much about this because at last time's festival, Keith Julian gave a very nice review of some of the work that's been going on. What you do is that the fast time is the rotation period, and then you can include either 1 or 2 slow timescales and derive a reduced set of PDEs. And I put some references down here for works that have looked at either the dynamo problem or just the straight convective problem, essentially by doing an asymptotic 2 timescale expansion. And the reason that this works quite well is because the state that you're doing your asymptotic expansion about is a fairly simple state. You have something to get hold of, which is not going to be true. There is going to be a small parameter in the solar dynamo problem, which is going to be 1 over the magnetic Reynolds number, but there's nothing really sensible to perturb about in that problem. Okay, So that's an approach which gets you somewhere in for a geodynamo problem. And again, Fausto mentioned this last time, that the problems for planets, they all arise in the momentum equation, I would say it's fair to say. And so you have this equation, and in general, the balance that you get, the leading order balance that you get, will leave some of these terms redundant. So for example, the inertia terms are very small. The Coriolis term is going to be very important. We're talking about rapid rotators. In a sense, pressure is always important. Buoyancy drives the flow. Viscosity is very, very small, as we've talked about. And where the Lorentz force enters into the balance, I think, depends on scale. And so you can get situations where it does enter into the leading order balance, or it doesn't enter into the leading order balance. And indeed, some planets are believed to be in magnetostrophic balance, where it does enter into the leading order balance. And some planets are believed to be geostrophically balanced, where the Coriolis force balances the pressure at large scales. But as you go to smaller and smaller scales, then you can get to more magnetostrophically balanced. And as I said, there's a very nice paper by Henri Claude and Nat Schaefer, and then there's a paper by Krista Sutherland et al., where they talk about what balances they think are occurring in the different planets. So in order to get all of that correct, given that we can't do direct numerical simulation, you have to pay particular attention to getting the separation of timescales correct and getting the balances correct. And that is a very difficult problem to do. Okay, so that's all I'm going to say about the geodynamo problem. Just remember that the problem is all to do with really the momentum equation. So for the sun, and indeed, if you're thinking about trying to do the dynamo problem for galaxies, the problem is somewhat different, and it really arises from the induction equation. And it comes from the fact that at high magnetic Reynolds number, a turbulent flow wants to, at least kinematically, put all its energy into very small magnetic fields, small scale magnetic fields. So magnetic fields on a very small length scale. And we're trying to understand that is really a lesson or a thesis in trying to understand the breaking of constraints. So the ideal induction equation has certain constraints, certain topological constraints that are respected, and the weak breaking of those constraints is trying to understand them is crucial to really understanding what happens at high RM in astrophysical dynamos. So there's a very interesting question: is what sets the irreversibility of these dynamos? Is it set by ohmic processes, or is it set by perhaps loss of information through boundaries? And I'm going to say a little bit about that a bit later on. And the reason that this is a difficult problem is that if it is ohmic processes that set the irreversibility, that arises at very small scales, and that is therefore a very difficult problem for computational physics to address. Okay, it's much easier to address irreversibility if it occurs at large scales. It also occurs possibly on very long time scales, and that again, similar to the reconnection problem, poses all sorts of problems. And as I was saying, really, this thing is either a dynamo or it's not a dynamo. And so it's quite hard to do some kind of asymptotic expansion whereby you get you can do essentially a well-defined asymptotic expansion about a state. Although there are some interesting approaches by Deguchi and some of his collaborators, which I think bear further investigation. Okay, so let's move on. So all of that is a kind of introduction. So it's not difficult now. I think it's very well recognized that it's not difficult to get dynamos that can put energy onto small scales. And really, I think any turbulent flow, even at high RM, will amplify magnetic field. And because these small scale dynamos, they simply rely on chaotic stretching and reinforcement of the field. And I think it's fair to say that any sufficiently chaotic flow has a tendency to generate magnetic field on the resistive scale. So remember, Rm in a star is something like 10 to the 8, 10 to the 9. And so the length scale associated with the resistive length scale is very small. So it scales like Rn to the minus a half. This is not the systematic behavior that we saw when we were looking at the sunspots at the solar surface. So I'll just show you this nice example, if you like, of a very well-known, very efficient small-scale dynamo. It's a cellular flow. I can play it. So it's a cellular flow. It's proposed in a Cartesian geometry. It has it can be described in terms of a stream function, and it's 2.5 dimensional in the sense that it has all 3 components, but only depends on 2 spatial dimensions. And so we have this cellular flow, and we have a vertical velocity, which is correlated with the cellular flow. I won't go into too much detail. This is called the Galloway-Proctor flow. And what you do is you take this nice cellular flow and you wobble it around. Oops, that didn't work. Why did that not work? You wobble it around, and this enables you to have chaotic particle paths, and therefore allows this thing to be what's called a fast dynamo, i.e. it's still going to be a dynamo at high magnetic Reynolds number. Now, the reason that people look at these so-called 2.5 dimensional flows that have all 3 components but only depend on 2 spatial variables is that you can, if you're just solving the kinematic induction equation, you can, that's making me a bit giddy, so I'll stop that. You can look for monochromatic solutions to the induction equation and calculate a growth rate, and you can essentially do a 2-dimensional calculation to work out the growth rate. So even though that your dynamo is really fully 3D, your magnetic field is 3D, you can actually work out the growth rate as in a 2-dimensional calculation. And what you find is that, as expected, the field is amplified on a resistive length scale, but this flow does remain a dynamo, a small scale dynamo at high magnetic Reynolds number. So let me show you what that means. So the field is amplified on a turnover time of the flow. It seems to be independent of diffusion as the magnetic Reynolds number gets large. And as I've said here, it relies on the chaotic stretching of the magnetic field lines by the velocity. Okay, and here we have a picture of the growth rate against Rm, and you can see that the growth rate shows no sign of going to 0 as Rm gets large. So it's a very good example of something that's working as a dynamo as Rm gets large. And this is sometimes in the literature called a fast dynamo. So here we go. So what happens as we start increasing the magnetic Reynolds number is that the kinematic growth rate, which starts off negative, increases to an asymptotic value as Rm gets large. And the nice thing about these kinds of 2.5D wobble type flows is that they get to their asymptotic regime, this kind of green part of the growth curve, for RMs not very much bigger than the critical RM. Okay. So what I'm going to insist on is that when one's talking about high RM dynamo, we must be kind of close to its asymptotic RM, the RM which makes its growth rate asymptotic for a small scale dynamo. That is when you're doing numerical calculations and you want to be at high RM, you really want to be in that regime. Okay, I didn't say too much about it, but if you go back to the Galloway-Proctor flow and examine it, you will see that that flow is helical. It's a helical flow. And as we'll see, helicity is going to be an important, or at least breaking a reflection symmetry is going to be an important constituent in flows being a large scale dynamo. So let me, So large-scale dynamos rely on a lack of reflectional symmetry. Of course, field could also be generated on a large scale just by stretching by a large-scale flow, but let's ignore that for the minute. So this lack of reflectional symmetry engenders correlations between the small-scale flow and magnetic field, and it leads to the generation of a net electromotive force. And this means that the phase between the flow and the field is going to be important. And this makes this kind of dynamo a more sensitive type of dynamo than a small-scale dynamo, which, as I've said, will exist in any sufficiently turbulent flow. And this kind of phase correlations and the notion of averaging and all of this was, of course, formalized in the very elegant theory of mean field electrodynamics, which goes back a long way, well over 50 years now. And so I'm just going to very quickly give a quick introduction to mean field electrodynamics, and then talk a little bit about what some of the problems are, and then I'll finish. Okay, so for mean field electrodynamics, we can split our velocity field up into a mean and a fluctuating part, and do the same with the magnetic field into a mean and the fluctuating part. I'm going to mainly think about the mean flow being 0, but you don't have to do that, of course, but it makes the analysis a bit easier. So then you write down an evolution equation for the mean field, the mean magnetic field. Of course, it's the mean induction equation. You expand out your U cross B term, the mean of U cross B, and of course you get a term which involves kind of like large scale interactions, mean interactions, but you also get this term which is the electromotive force, the EMF term, which comes from a fluctuation averaged interaction. So E is U prime cross B prime bar. So sometimes that's called that's the eddies correlating with the eddies to give you a mean electromotive force. Okay, well, that's not much use to you unless you know what B prime is doing. So of course, to write down the evolution equation for B prime, you take your full induction equation, you subtract off it the evolution equation for the mean, and that leaves you the evolution equation for the fluctuations. And then you write down the evolution equation for B prime, and there are mean fluctuating terms, there are fluctuation mean terms. This is a linear term, so that's okay. And then there's this term which arises through the fluctuation interactions leading to another fluctuation. And this is sometimes called the pain in the neck term, or for fluids problems, it's sometimes called the eddy going to eddy nonlinearity. Okay. And so all is well and everybody's happy if you can ignore this term, okay, this term G. And there are lots of approximations, so-called quasi-linear approximations, and I'll talk a little bit about that on the next slide, that will enable you to neglect that term in favor of the other terms. So if you can do that, then you're going to be able to solve your fluctuation magnetic field equation via essentially linear methods, Fourier transform, Laplace transform type methods. If you keep this term in, then of course it's a lot more difficult. And quite often there are ways of approximating this term using closure theories or something like that, which I'm not really going to talk about. What is true is that you can write EI, the electromotive force, as a linear kernel, an integral kernel differential equation. Sorry, I didn't say that very well, but you can write it in terms of the mean field, and therefore once you impose a difference in time in spatial scales, a separation of spatial scales, you can get this famous expansion of the electromotive force in terms of the mean magnetic field and the gradients. And this is the famous alpha effect term of mean field electrodynamics, and this is a turbulent diffusion. Okay. Okay, so just going back to what I said earlier, to set G is equal to 0, or if you set G is equal to 0, you can do that in a couple of limits. You can take Rm to be small, in which case it simplifies further. The fluctuating induction equation simplifies further. Of course, this is not a very relevant limit astrophysically, Rm being small. As I said, Rm is 10 to the 8th, so that's not much use. Or you can take the correlation time of the turbulence to be small, okay? And if Rm is, if the correlation time of the turbulence is small, and even if Rm is bigger than 1, you can write down the solution for B prime in terms of B bar, okay? And you can get a closed system. So both of these are, this is called first order smoothing. Both of these are essentially doing a quasi-linear approximation to the Dynamo problem. Okay, so I'm not going to go into any detail, but when you do this, if you use first order smoothing, then you can relate these transport coefficients alpha and the turbulent diffusion to the statistics of the actually the fluid velocity and the vorticity. So here alpha is related directly to the helicity of the flow. And this is a sign that alpha is, this generating term is non-zero only if there is non-zero helicity or there's a broken reflectional symmetry, whereas the turbulent diffusion is related to the essentially the kinetic energy of the fluctuations, and therefore is more robust. It's a much more robust process. This one works even if there's no broken symmetry. Okay, so that's a very quick introduction to mean field electrodynamics. But the thing to take out of it is that helicity, in this case kinetic helicity in the flow, is important for generating large scale fields. Okay, so the small scale dynamo that I talked about, the Galloway-Proctor flow, it has all the ingredients required to be a large scale dynamo. So it has lack of reflectional symmetry, and that should lead to the generation of a mean EMF. But when you do the calculation, all you see really is a small scale field. So as I've said here, a high RM for flows in its asymptotic regime, the large scale magnetic field generated by an EMF is usually completely dominated by the small scale fluctuations. And so one of the things that people have been thinking about is how to get the large scale generation mechanism to work and overpower, if you like, the tendency to put energy in the magnetic field at small scales. And one of the things that we haven't considered so far is the fact that possibly most of these things are in a sheared environment, most of these dynamos. And so it's worth investigating the role of shear in promoting the large scale over the small scale. So you can promote the large scale dynamo over the small scale in two ways. You could use the shear to hopefully promote the large scales, i.e. give you a larger EMF, or you could use it to try and suppress the small scales. So a few years ago, Fausto and I tried to do this. We took the Galloway-Proctor flow and put it on a very small scale because we wanted to get a good separation of scales in our box. We added a shear flow, okay, a shear flow of this form. So this is now a large scale flow. And what we wanted to see was whether adding this shear flow to a Galloway-Proctor flow could promote the growth of large scale or systematic fields. And I actually have talked about this at the festival a while back. And what I'm going to talk about today is progressing this into the nonlinear regime. Let me just show you what happened in the linear regime. So just to say that because we're using the same trick as Galloway and Proctor did, where we're doing a 2.5 dimensional flow, it's possible to get to very high magnetic Reynolds number. So the magnetic Reynolds number of the shear here is it can go up to about 10 to the 5, and even the magnetic Reynolds number on the small scales of the small scale cellular flow still gets up to about 10 to the 3. So these really are in the green zone, if you like, near the asymptotically relevant limit. So let's imagine we have no flow, and then we just get, so for no shear, sorry, not no flow completely, no shear, we just get this filamentary field generated by the cellular flow at very small scales. So this is field as expected on the scale of Rm to the -1/2, okay? So the length is comparable to the scale of the velocity, the length of these filaments, and the width is controlled by diffusion. I'm not certain what's happened to my formatting there. And the overall pattern changes on the turnover time. So if we were to average this field over, say, one of the directions, say X, we're interested in average fields, we wouldn't get very much in the way of systematic behavior. Remember, this is an exponentially growing field, so we've removed the exponential growth. We don't see any systematic large-scale behavior. So I've averaged over X, and I'm plotting Y as a function of, B, X average as a function of Y and time. And it's very hard to see any kind of systematic behavior because there really isn't any systematic behavior. Okay. So what happens when you add shear? So in order to investigate this, we constructed two different types of Galloway-Proctor flows. One where it did have some helicity, some net helicity, and one where it didn't have any net helicity when you averaged over time. And we wanted to see how these things interacted with shear. So I'm going to show you the same picture when we have shear for two cases, one with helicity and one without helicity. So here are the pictures, and you can see here what we can see in the case where the small scale flow has helicity. We have these nice dynamo waves, which are located in the regions of strongest shear. Because we were doing it in a periodic box, we had two regions of strong shear. We have this alternating, very systematic spatio-temporal behavior. When we had a non-helical flow, of course, we still get field generated, but it's very hard to see any of the systematic behavior. Now, this flow does have helicity, even this bottom flow does have helicity at any given time. It's just when you average over time, it has no helicity. And so there are periods where you believe you can see kind of wave-like behavior, but it's certainly nothing like as systematic as the behavior here. And what has happened is that the shear has acted so as to suppress the fluctuations in the distribution of the magnetic field, and it hasn't really changed the mean EMF very much. And you can see that if you have a look at the distribution functions for the EMF for different shears. So for zero shear, we have this black curve here, and the EMF is bouncing around all over the place. Okay, it has a well-defined mean, which in this case is negative. It's about here, but there's lots and lots of fluctuations in the EMF. As you increase the strength of the shear, the mean doesn't change very much. It does change a little bit, but the distribution is much tighter around the mean. And so what we're doing is we're really controlling the fluctuations, and it's controlling the fluctuations that enables you to see the large scale field. Okay, I have about 10 minutes left, so I shall speed up. Okay, but mean field theory, it certainly doesn't get everything right in the kinematic regime. Okay, so this is kind of interesting, I think. We know that for kinematic dynamos with a small scale flow and acting as a small scale dynamo, the growth rate of the dynamo is controlled essentially by the fastest overturning eddies, which have Rm of greater than the critical Rm. And so the growth rate of these dynamo waves, because they appear as part of an eigenfunction, is controlled by the essentially by the eddies, by the fast going eddies that produce the small scale magnetic field as well. Okay, so mean field theory would say that the growth rate is essentially determined by the alpha effect, but that's not correct. It can't be correct. However, the thing that mean field theory does get right is the frequency of the waves, because they really are a large scale dynamo phenomenon. Okay, so the shear breaks the isotropy of the filtered equations, and it acts to perturb the frequency of the solutions away from zero. And so that really is controlled by the change in symmetry of the large scales. And so mean field theory, although it can't get the growth rate correct, it can get the frequency of these modes correct. And that gives you hope for when the dynamo has saturated. If the dynamo saturates, then we're no longer interested in growth rates, but we may be interested in frequencies of nonlinear solutions. Okay, right. Let's go on to nonlinear approaches. So far, all I've discussed is the induction equation. What do people do nonlinearly? Well, there's a lot of numerical simulations of DNS of dynamos. But if you want to do something theoretical, then of course you have to appeal to some kind of closure theory, usually. And the nonlinear approaches usually involve some type of turbulence modeling. And so, of course, you know, going back, they've used all of these approaches, quasi-normal modeling, where the PDF of the nonlinearity is assumed to be Gaussian, but there's a problem that this may lead to lack of realizability. So of course, this was fixed up by Orszag to produce eddy-damped quasi-normal Markovian type modeling. So there's a scale-dependent damping term, and so there's been ways of elaborating on this. It's the so-called minimal tau approximation. So this EDQNM is a very nice approach. However, what happens is that you need to prescribe an eddy damping rate for this in order to use EDQNM, and there's no real feedback of the magnetic field on the eddy damping rate. And so that is a problem. It's very interesting to speculate on what effect the magnetic field does have on the eddy damping rate, and I think it's fair to say it's not going to be an insignificant effect. You could use approximations such as the DIA, the direct interaction approximation, and what this involves is deriving a closed system of equations, and you get the equations for the correlation function and the response function of the turbulence. And this has actually been extended to two-scale direct interaction approximations by Nobumitsu Yokoi and his supervisor. And there's a very nice review by Nobu in 2019, which talks the way through this. And that allows you to do two-scale, essentially, mean field theory using the direct interaction approximation. And you can do some weak inhomogeneity that way. The central problem, though, of nonlinear dynamo, turbulent nonlinear dynamo, is really, even if you can generate a large-scale field kinematically, what is the amplitude at which that magnetic field saturates? If it saturates at a very low level, that depends on the magnetic Reynolds number, then it's not really going to be very useful as a dynamo, because we want to get mean fields that are, observable and strong. And the problems with mean field theory, or go back a long way to postulating, even if you get this alpha effect, how does this alpha effect depend on the strength of the mean field? And simply put, you could imagine a kind of quenching formula for the alpha effect, whereby you take the kinematic value and you quench it and it gets quenched or systematically affected when the mean magnetic field is of the order of the equipartition energy of the flow. And that would be fine if we could get large-scale magnetic fields of the order of with the energies comparable with the energy of the flow. That would be great. However, there are very many arguments that say, well, it's not quite that simple, and the strength of magnetic field, mean magnetic field that you can get to, is multiplied by a factor, Rm to some power, magnetic Reynolds number to some power, when it comes into the quenching formula. And so this would mean that the saturation would occur for much weaker fields. And the weakness, if it's Rm to some power smaller, then that could be catastrophic. And this is why it's called catastrophic quenching. So there are various very good physical arguments as to why this may happen. And there are various, I would say, not so good, for reasons I'll explain later, analytical arguments as to why this may happen. And most of these involve taking evolution equations for the magnetic helicity and also evolution equations for the electromotive force. And I'm not going to go into any details. And combining them with a if you like, a prescription from EDQNM, so this is the prescription due to Pouquet et al. For the alpha effect, and combining them with an evolution equation for the magnetic helicity here, the total magnetic helicity, and deriving quenching formulas that look something like this. Okay, and the best example I know of this is a paper by our fearless leader, Pat, where they did this. What I want to pull out of this is that the magnetic helicity, and we'll come on to this in the final 2 minutes of my talk, the magnetic helicity changes essentially because you're breaking you're introducing irreversibility to the flow, and you can either introduce this ohmically. Okay, so here's a term which looks like an ohmic introduction of irreversibility, or you can introduce this through flux terms in the equations. Okay, so I've said this on the next page. So it was argued that fluxes of helicity can potentially alleviate the effects of this catastrophic quenching. So this all comes down to the irreversibility of the flow. And so if you're only allowed to introduce irreversible processes on an ohmic timescale or through ohmic processes, then what's argued is that if you start off with some very small, all your magnetic helicity in the small scales, it's very hard to get it into the large scales except through those ohmic processes. And so this will either not occur or happen on an ohmic timescale. However, if you manage to lose helicity, magnetic helicity, through the boundary of your calculation, so you're losing information through a boundary at a rate independent of the resistivity, then you might be able to get the introduction of large-scale magnetic helicity into your system on a timescale that you can live with. Okay, so just very quickly, what we try to do is we try to set up a numerical calculation similar to the one we did before, but this time in the nonlinear regime. And I'm not going to talk very much about the kinds of forcing we use. We forced a flow which looks a little bit like a Galloway-Proctor flow again, with a shear. But the key was we looked at the evolution of the magnetic field in two cases. One where magnetic helicity was allowed to leak out of the domain, and one where the no helicity flux was allowed to leak out of the domain. And we tried to work out which one of these could produce better large-scale magnetic fields, or more systematic. So when you're talking about evolution of magnetic helicity, you have to consider what gauge to do your calculation in for the evolution of the magnetic helicity. So we chose the winding gauge, which was introduced by Pryor and Yates. So this is very good for Cartesian calculations. So in contrast with the Coulomb gauge, for which div of A is equal to 0, what we're doing is the horizontal divergence of A is equal to 0. The reason that this is a nice choice of gauge is that it has a, if you like, a kind of physical interpretation. So for open field line configurations, the winding gauge is essentially a measure of the mutual winding of field lines about each other. And this nice gauge and the properties was introduced by Chris Pryor and Anthony Yates in 2014. And this is the mutual winding is a topological invariant for all deformations that forbid self-crossing. And the helicity in the winding gauge essentially gives you the average pairwise winding of field lines. So it gives us a nice geometric interpretation to our topological invariant. Okay, so I really don't have time to go through how we calculate everything, so I won't do that. Here's the evolution equation for the helicity, for the magnetic helicity. And this is what we're going to try and keep track of. The magnetic helicity evolves essentially in this gauge owing to 5 processes. There's let's start off with the easy one. There's this one, WD. This is just the ohmic dissipation of the magnetic helicity throughout the volume. So it looks, there's a term there which looks like J dot B. There are different fluxes. So there's a diffusive flux out of the domain. There's an ideal flux out of the domain. And then there are some terms, sorry, this is another diffusive flux out of the domain. Then there's a term which relates to the complicated geometry in which we're doing the calculations, which should be familiar to all the plasma physicists, I guess. So we're doing this in a calculation with periodic boundary conditions in the 2 horizontal directions, and therefore there's some self-interaction terms which come from working on a torus. Okay. So we did lots and lots of calculations. We did some with and without shear in periodic and non-periodic domains at high PM, and for some for PM of order 1. So some of them we really fixed the Reynolds number to be small and took the magnetic Reynolds number large, which is, you can essentially then split up the flow into the bit that's driven by the magnetic field and the bit that's driven by the forcing. Or you can take both the Reynolds number and the magnetic Reynolds number large, and the flow then is very turbulent. So just let me, okay, I really don't have time. Let me show you some kinds of evolutions. So in periodic domains, you can get large scale fields, even with no shear actually in this case. You can get large scale fields, but these emerge on an ohmic timescale. And so these are very well understood. They've been seen a lot before. You get this large scale Beltrami mode, which is essentially a force-free field. And so because it's force-free, it doesn't really act back on the flow. It grows on an ohmic timescale. It's one of these, essentially, you can think of this as almost like a condensate, which gets generated by essentially continual pumping of energy from the small scales. Even if it's very weak, there's nothing really to oppose it. So these are systematic large-scale fields, but they're not really the kind of systematic large-scale field we're interested in, because they emerge on an ohmic timescale. And you can see why they emerge on an ohmic timescale, because there aren't any flux terms in the period domain. So the only thing that can change the magnetic helicity is our body force term here, WD. Oh, that's my alarm telling me to shut up. Okay, so I'll shut up in a minute. If you have a case where the magnetic helicity is allowed to leave the domain, you can get very complicated dynamics, which I'm not really going to talk about today. You can get some large-scale dynamo waves. You can get some with a formal mean field. You can get oscillations because the shear flow can get acted back on by the magnetic field. So these are like predator-prey type oscillations. So we can see them here. So this is systematic large-scale fields being generated. But what we're really interested in is what is it that's contributing to the changes in the magnetic helicity, or the breaking of reversibility. So we calculated all the fluxes, and okay, I'm not going to have time. Let me go to this summary figure here. Okay, so you can calculate how much is carried by the diffusive flux, and this is just a schematic, versus how much is carried by the ideal flux out of the domain. And the answer is, for the magnetic Reynolds numbers that we've been able to investigate in 3 dimensions, it's the diffusive flux that seems to win. And so the processes that are taking place here are really being controlled on an ohmic timescale. What is the case, though, is that the diffusive flux is changing with Rm at a faster rate than the ideal flux. So if you were very optimistic in your outlook, you might draw in these dashed lines and say there is an Rm at which the ideal flux will take over from the diffusive flux. And that kind of behavior has been seen before in this paper by Del Sordo et al. It's simply impossible to get anywhere close numerically to this crossover point, as far as I can say. So what we're thinking about now is perhaps playing around with, doing the thing you should never really do, is playing around with the thing that sets the irreversibility in the induction equation, and trying to see if you can get this crossover happening further down here by perhaps putting in a hyperdiffusion or a magnetic friction, or perhaps a scale dependent breaking of the reversibility. I don't really have time to say very much. Inhomogeneity may also play a role. If you can store your magnetic field away from its region of generation, then that may also play a role. Or if you can perhaps reconnect field lines across the equator, which was a kind of idea from Weinstein, Parker, and Rosner going back quite a long way. Okay, so let me finish. Apologies for overrunning. So just to say, small scale dynamos, they put energy at the resistive scale. They rely on exponential stretching. And fast dynamos are small scale dynamos that work as Rn tends to infinity. Large scale dynamos, they're more subtle. They rely on breaking of reflectional symmetry, and shear can help the large scale win out of the small scale by suppressing the small scale magnetic fields. Now, catastrophic quenching, this thing, it can be understood in terms of helicity conservation, but I think it's wrong to think of helicity conservation as causing catastrophic quenching. It's really helicity conservation is a sign of reversibility, and it's the fact that you can only get irreversibility on slow timescales that leads to catastrophic quenching. It's not clear at the minute that helicity fluxes from a domain can alleviate catastrophic quenching. And I think you need more efficient dynamos or to play around with the diffusive processes to understand really what's going to work. Okay, so apologies for overrunning, and I'll stop there.
Okay, thanks a lot, Steve. That was great. No worry. So it's time for a question. Well, I haven't seen. Yeah, there's. Well, I see Pat and then Guillaume.
Guillaume was first, and then me.
Okay, I didn't look at the people. So since he was the host, I thought that. Well, Guillaume, please.
Well, thanks.
We always yield to the Legion, so.
Thanks a lot, Steve. Coming from MFE, you probably have an idea of what I'm going to ask. We know that should you impose from the outside shear, or should you get it self-consistently, you probably have, in the end, very different results. Yeah. So if you were to redo, or think of a way to redo your Direct series of runs with not an imposed large-scale shear, but somehow you get a self-consistent large-scale shear through another equation or through other processes. What's your feeling about the outcome and how that may help?
Yeah, I think that's a very interesting question. I mean, of course, this is not self-consistent shear. You just put a forcing in the momentum equation that kind of mimics the shear kind of shear you like. From the point of view of solar physics, we know that there is shear in the sun. So it's not unreasonable to say, well, we don't quite know self-consistently how that shear got there in, say, the tachocline or in the convection zone. But, as far as whether it can generate a large-scale field or not, I think it's fair enough to impose it. You're right that if you really wanted to get a very self-consistent model of the magnetic field, be it large-scale, interacting with the shear, then of course you should get a self-consistent generation mechanism. I think it's fair to say that the Lorentz force term is only going to start interacting back on the shear when the field, if you get a large-scale field of a sufficient strength. And so in a sense, once it starts interacting with the momentum equation, you've won, because for it to interact with the large-scale flow, it must have got, you probably have got a large-scale field which is doing something, as opposed to just switching off the small-scale flows. So I think you're right. It's something we should worry about, but it's kind of a bit further down the expansion, if you like. We're still doing order epsilon calculations, if you like. That's probably an order epsilon cubed, because at the minute we can't even get, large-scale fields. As Chris Jones so adequately puts it, we can't actually solve the induction equation in the right parameter regime.
Spot then.
Okay, so I had three things, one of which was exactly the same as Guillem's, but I would push a little harder. He's much too lenient on you.
Okay.
Which is, in the study of shear suppression of turbulence that has occupied us in fusion for the last, 1,000 years or so now, you really see, and it's still, the message hasn't got to people who don't want to face reality that often means shear just does jack squat, right? And nothing happens. Okay, and what happens is the modes adjust to dodge the shear. Okay, so one possibility is a somewhat more interesting structured profile, or another possibility. Then, of course, there's the whole zonal mode business. But it begs the question, to be a little more specific then, if you can take our beloved beta plane MHD, which of course is 2D, but add the minimal third dimension, and I think it's called the Roberts model, if my memory is right. Wouldn't that be a wonderful test case to examine this self-consistent versus external thing?
Yeah, you could certainly, that is yes, that would be an interesting thing to look at. I think that's right, because there you're getting the shear self-consistently generated from the interaction of rotation and the turbulence.
Right.
Generates a shear. That shear is presumably going to act back, and of course we can put in a shear, if you like, this Struhl number, if you like, we can get that to whatever we like. The question is, what is a realistic ratio for shearing times to eddy turnover times and all of that stuff? I agree. You would like to do something like that. The problem with imposing that as a model, it certainly kind of works kinematically. But then when you start thinking about doing things three-dimensionally, which, non-linearly, you have to go to 3 dimensions. And so you want something which remains a robust generator of shear, even when things are 3-dimensional. And of course, spherical Dynamo codes can do this, but of course they have their own problems getting to high RM. So there's always a trade-off between, being realistic and getting to high RM. So we threw away all kind of realism for getting to high RM, but that's not necessarily it. Yeah.
Okay. A comment, I mean, on the thing about the effect of the magnetic field on the eddy damping, I believe Pouquet, Frisch, and Leyra actually addressed that issue in some depth.
They
put
did.
it politely.
They did, but it's still not clear to me that what was said is correct at high RM, because as you know,
true.
Yeah, no, absolutely, yeah.
I mean, but there is at least a starting point. I mean, the next step, of course, would be that paper had, would be some kind of very detailed, it's easy to talk, very detailed simulation comparisons to the predictions of that paper.
Yeah.
That's something that I've been in uncountable infinity of meetings on this subject, and everyone says, oh yeah, we got to go look at that carefully, and no one ever does.
Yeah, I know why, because it's hard to get to high RM. I mean, it just is. But you're right. You're right. Perhaps the time is ripe for looking at that. Yeah.
And last but not least, on the matter of the how do you get off the hook on the helicity flux and all that? I mean, inhomogeneity is a good idea. I like that. And an obvious thing to me has always been some kind of inhomogeneity in the spectral intensity, which could be tailored maybe by inhomogeneity in forcing or dissipation. Yeah. And again, that's something the fusion community has played around with a great deal, is, symmetry breaking by spectral intensity gradient as opposed to things like gravity or curvature, gravity rotation, blah, 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 the usual things.
Yeah.
I mean, and anyone ever look at that? And maybe a good place to start would be with the two-dimensional problem with the transport of A squared, as we discussed, I'd say, in San Diego. And,
yeah. I mean, I think, you're right. Introduction of inhomogeneity, it brings in extra terms. That's true. And some of this has been looked at, as I say, within that DIA approximation by Nobumitsu Yokoi. So it has been looked at within the framework of that approximation, I think it's fair to say. But that's an approximation, so quite whether that works at high RM, I don't know, is an interesting question.
Thanks.
Okay, I think David was next.
Yeah, thanks. So Steve, in your third point here about shear can help large scale win out over small scale. So I'm just trying to get my head around the various scales, because if we were doing 2.5D dynamos, then the large scale field is really in Z, isn't it? I mean, that's what the alpha tensor gives you.
Yeah. Well, yes, if you that's true. But what we're doing these, okay, yeah, sorry, I should have made that a bit clear. We're doing these calculations at fixed KZ.
Yeah, no, but if I could just finish my thoughts. So within this particular sort of flow which we all use, that's the large scale is really a small k.
Yeah.
KZ.
KZ, that's right.
And then you're introducing introduction of a flow is essentially large scale, presumably in whatever X or Y, whatever it was.
Yeah, it's like Y. Yeah.
So it's a kind of interesting in this geometry, you've got a large scale in one direction, but the large scale field is in the other. So I'm just wondering, don't really have a very clear question.
No, yeah, I see what you're saying.
Put together, how might it?
So you're right. So yeah, when we do these things, you think of these things as like, the large scale field growing like alpha b minus beta k, alpha k minus beta k squared, where k is that wave number in the Z direction. That's absolutely right. And And what we're taking is as our large scale is we're averaging over the zonal direction, which is different. So it's really a large scale in that direction. So we're looking for dynamo waves, which are I mean, they're really still functions of Z. So there's a KZ still there. So they're traveling in that direction, and Y. So and the direction of the shear, or the variation of the shear, is in the Y direction. So it's a different type of large scale, a different type of averaging. That's right. Yeah.
Okay.
Yeah.
Can I ask another? In the famous Pouquet formula, what is
Yeah.
your interpretation of U, omega, J, and B?
Yeah, good question. Okay, so I interpret okay. I interpret these things as statistical averages. And so I would say that these are the saturated values of whatever you just said, U, omega, J, and B.
Right.
And of course, that's then an approximation. It's the EDQNM approximation, right? So you take your PDF for U, for omega, for B, and for J. You calculate the dot products, and then you take the average of that with the minus sign in. And I mean, as you know, we've thought about this for a lot. What it means if these things are spatial averages, I'm not absolutely certain that it makes sense. As you know, I mean, you have to think of these things as perturbations about the saturated state of a dynamo, perhaps. I don't know, but within the realms of just ensemble averages, I think it's okay if you just do it that way.
Yeah, I'm not very keen on ensemble averages.
Yeah, well, who knows? Yes, yes, it's okay for ergodic flows, but yeah, I agree. Yeah.
Okay, could I ask just one more while I'm here?
Sure, if it's okay with Yannick. Yeah.
The gauge.
No, that's fine. Go ahead.
The gauge issue.
Yes.
So when you talk about, what do you mean when you talk about small scale helicity and large scale helicity?
Yeah, that's also a good question. Okay, so I think the best way of working these things out is actually the way Pryor and Yates do, where they do essentially kind of like wavelet analysis of the helicity. And so because you're doing a wavelet analysis, you can get things localized in space and in wave number space. So yeah, I think you can get the wrong answer if you just do, let's say you do a Fourier, you take the magnetic helicity, you do a Fourier transform, you work out the power in A dot B as a function of K, say. You can mislead yourself as to what you mean by small and large scale. What you mean is you have this thing which is a function of wave number, and it's at high wave number or low wave number.
But how do you get around? Yes, I can see you can do it, but it worries me that you choose another gauge, and you choose a gauge with lots of small scale stuff, and you or large scale stuff, whatever. You've made everything very different, but you haven't changed the physics.
Yeah, yes, but the hope is that when you do your evolution equation for what I mean, okay, so people talk about this kind of like as there's this transfer between large and small scales or whatever. And you're right, if you change your gauge to put in lots of small scales, then you might misinterpret something which is just, I don't know, something for is putting energy into the small scale magnetic helicity. But I think if you do all your calculations in a gauge that you've chosen to start off with, then if you get some large scale field out the end, then associating that with large scale helicity is fine, so long as it's true. You can always change what you mean by, you know, whether this field has small or large scale helicity by essentially changing your gauge, or in the winding gauge, unwinding, you know, you can unwind things. But if you don't allow your gauge to change as your calculation is going on, then I think, you know, things can move from what you might think of as formerly small scale to formerly large scale.
But yeah, maybe. I mean, I you know, if you were being perverse, you might come up with a gauge that did change with time, that didn't change the physics, led you into different conclusions, I guess.
I guess that's possible. I'm not, yeah, maybe that is possible to have a gauge that changed with time. Then you probably have to worry. Yeah.
Well, I've always been worried about gauge, but anyway, okay, thanks.
Yeah, okay.
I think Xavier was next.
Hi, Steve.
Hi, Xavier.
Good talk. I have a probably naive question on the story of the helicity fluxes that could save the day. I think you mentioned at some point that this could be done via, you know, helicity losses or injection, I don't know, at the boundary of your simulation domain. So this, by the way, has been done in tokamaks, by the way, to produce the poloidal magnetic field. But how would this work in the astrophysical subject context? Sorry, I mean,
yeah.
How can you, for instance, for a galaxy or?
I think I missed the end of your question, Xavier. Are you still? Sorry, can you just repeat the question? You said.
I was just asking. The question is, in the astrophysical context, that is a galaxy or, you know, the sun.
Yeah.
What would produce these fluxes of helicity at the boundary, for instance?
Okay, so the people who are very keen on this, and I'm not necessarily one of these, but they for the sun they may look at things like coronal mass ejection. So you get these reconnective events on the surface of the sun, which shoot out plasma, and they really do change the topology of field lines. And so you might say, okay, this is kind of a way of losing helicity. And so there is an industry of people calculating helicity losses from the sun. In galaxies, they have these outflows which carry helicity with them, that kind of thing. The question is, how can you lose enough helicity without losing all your flux as well? So what you need, I mean, it's quite clear that if you take your complicated magnetic field lines out of your region of dynamo action and reconnect them quickly, or get rid of them, or do something with them to get rid of them, then you've got all the irreversibility you want. And you know, my question. Oh, sorry, my dog is. Apologies. My question then is, you know, how do you? I mean, if you like, one is a surface. One scales with the surface area, and how does the convection at the bottom of the convection zone suddenly know that there's been a little bit of helicity loss at the surface of the sun? I mean, it will know on a long enough time scale, but I mean, and maybe statistically speaking, on a long enough time scale, everything's okay. But the other thing I didn't really say is that maybe it's not. It doesn't really matter. Maybe if you start off with a large scale field in the first place, then all you have to do is maintain it. You don't have to get it from, you know, if you like, an inverse cascade or a kind of direct generation of a large scale field from small scales. So it might be that some of these dynamos, which people call essentially nonlinear dynamos, they're kind of better because all you have to do is maintain the magnetic field on the large scale, but have it have a evolution on a short time scale, which is possible. Yeah.
So what you say is that self-sustainment would require a moderate amount of helicity fluxes at the edges, right? Or,
yeah, because you've already got all your self-sustaining a large scale field. You've already got all your field in the large scale.
I see.
So you know, so maybe that's the answer. I mean, I don't know. There are lots of well, not some theories where the dynamo magnetic field is generated by essentially an instability of the large scale field. So you have a large scale field, it goes unstable, that drives a small scale field and flow, and then you can say, well, those are quite likely to be correlated, a bit like the reverse field pinch, right? In a sense, there's an instability, you know, these things will produce an EMF, and maybe just gradually self-sustaining these large-scale fields is not a problem. Remember, these are weakly dissipative, so maybe it's not too difficult to do. But then you have to ask, how do these things keep working if you've got turbulence there as well? So it's not trivial. Yeah.
Thanks.
Thanks, Xavier.
Hi, Hong, then please.
Okay, hello. My
Hello.
name is I'm struggling with the concept, the basic concept of dynamo. Is the dynamo process a turbulent process? It's turbulent.
Okay. Well, the ones I've described are turbulent. They're turbulent processes. However, I just described a laminar type of dynamo, which could work where, as I say, you have a field, it goes unstable, it produces a, you know, it interacts with, say, rotation to produce, say, a net handedness. So the instability will generate an alpha effect, almost like a laminar alpha effect that sustains the field. The fact is, though, that the flows we're looking at in astrophysics, they're always turbulent. I mean, they always seem to be turbulent. And so, you know, you want the mechanism, whatever it is, to work when there is turbulence. Whether it's necessarily it's turbulent flows that generate the dynamo. In the ones I've described, it is turbulent flows that generate the dynamo, but that's not necessarily the case, or doesn't have to be the case.
How about the magnetic power spectra? It's similar to the Kolmogorov law.
Oh, okay. So
different in index or something different, completely different structure.
Yeah, so the magnetic power spectra, obviously it depends whether you're in the linear regime, the kinematic regime, where the field is just being passively generated by the flow, in which case, I'll see if I can get this right, the spectrum looks like k to the 3/2, so it gets bigger at high k, right, because it's putting all the energy at the resistive scale. But then as nonlinear effects take place, it really depends on the, well, there are various ideas, but for example, the magnetic field could come into equipartition with the velocity field that's causing it. And so it might just take on the same energy spectrum as the flow. If you equilibrate scale by scale, then that might be the case. It may go to super equipartition at certain scales. So that I think that the power spectrum of the magnetic field really depends, I believe, on the form of flow that's causing it. So it would be very different, say, for something that's rapidly rotating than you know, homogeneous isotropic turbulence, for example.
Do you think is that possible for the all kind of the dynamos eventually, when they saturate, produce a magnetic power spectra similar to the Kolmogorov?
It's possible for a field to get a, yeah, you could easily get a field, a dynamo generated field that has a Kolmogorov spectrum. Yeah, depends on the form of the flow that's generating it. I don't see any reason why not. But as I say, it depends on the forcing and the flow, and yeah.
If I say the dynamo is a reverse energy cascade, do you think do you agree or disagree?
Okay, so you can think of the generation of large scale fields as an inverse cascade in the magnetic field. that's definitely a process that might be going on in large generation of large scale magnetic fields. There may also, and everything I talked about today is kind of like a direct driving of the larger scale. So it's like a non-local cascade. So it's like a k equals 10 interacting with a k equals minus 10 to give me a k equals 0. So it's like the equivalent of well, it's the EMF. It's the equivalent of a Reynolds stress term in the hydrodynamics. Just like in hydrodynamics, you can get inverse cascades, which are local or non-local in K space. I think you get the same effect in dynamos.
Okay, thank you.
Thanks for your question.
But then now a few more questions.
Okay, I wanted to go back to the helicity flux since, of course, as you well know, I've been bashed over the head with that for quite a while. It always seems to me that just to shout in a loud voice helicity flux through the boundary is content free.
Yes.
To get back to Xavier's question. And really, there's a huge, not to sound like the Donald, difference between the case whether there is reconnection at the boundary. In other words, do you magnetically disconnect the crap that goes out from crap that stays in or not, right? And this, the self-appointed high priests of the helicity flux never face this issue, is something I've known. And it related to that, you know, in the RFP, of course, you can cast the Taylor song and dance in terms of a flux of a kind of, I mean, helicity density is dangerous, but you can kind of, in a woolly, as the saying goes, way, you could think of it that way because of the symmetry. But you have a boundary again. And by the way, you have a very cold resistive boundary. The temperature goes down, right? So the stuff that goes out is going to be disconnected, right? So that's one reason of many why the RFP works so nicely.
Yes.
But any comments on that? The question of boundary reconnection.
I mean, I mean, I don't really have a comment except to say you're right. I mean, reconnection is the key. I mean, somehow you have to change the topology of the field lines. You know, you have to. Yeah, that's exactly right. And so, as you say, whatever you call them, the high priests of the helicity flux. I mean, if you're, as I said to, I think, Xavier, you know, if you're carrying stuff out of the domain, it's no use carrying stuff out of the domain if then you just let it fall back into the domain. Right. You have to reconnect it and get rid of it. I mean, you know, you have to somehow get whatever's left to be different to what was there before. Otherwise, it's a reversible process. And so, as with many things, I think in a sense, reconnection or understanding quite what can, if you really believe this is the way that these dynamos work, you know, it's the key. It's like, how do you get these things to change, having these things as invariants on a time scale that you can live with.
Right, of course.
Yeah.
I don't see other hands, but maybe I have one or two questions. The 11-year cycle is something which is regarded as a critical manifestation of the Dynamo process, leading to the generation of the large scale and mainly dipolar magnetic field, or is it something more critical, which is which goes along with the Doppler magnetic field? If you have one, then you have the other. What is is there a consensus on this, or?
I'm not certain I understood the second. What was the second option, Yannick?
Oh, either if you have the dipolar magnetic field, then you have the butterfly diagram, and they come both at the same time, or you can have one without the other.
No,
what the interaction between both?
okay, okay. So from a if you like, from a bifurcation theory point of view, you know that once you've broken the symmetry, the dynamo waves have to travel in one direction or the other, and so they have to travel either towards the equators or towards the poles, and so so if you believe shear is important, that leads to a kind of butterfly type effect where these waves travel. Okay, so that's known. However, I mean, I'm not quite certain how to relate that to the the dipole field is the largest scale of field, I mean, that you can get, and so it's that component at least that we see in the sun. Now there are other stars we can observe where, you know, we can't quite tell the topology of the field, but we know that they have cyclic behavior. And so it doesn't have to be like an 11-year period. It could be like a 3-year period or a 10-year period. And one would imagine that if differential rotation is important in those stars, then they will have propagating magnetic fields of the butterfly diagram. Now, I should say that there is a theory that the propagation of these dynamo waves is absolutely nothing to do with kind of like mean field electrodynamics dynamos. Is to do with that there's a meridional flow which bodily moves the field downwards at the base of the convection zone, which happens to have the right phase speed, if you like, to carry the field. So I'm not certain you can link the existence of an 11-year period with anything. I mean, in one case it comes from a turbulent transport coefficient. In the other, it comes from the strength of a meridional flow in the sun. So there are two very different theories for that. I don't know if that answered your question.
Yeah, definitely. Well, yeah, and maybe also a completely naive question, but how far are we from measurements that would help discriminating between the various theories, either measuring the magnetic field or the getting more properly the either the spatial structure of the flow and the time dynamics?
Yeah, okay. So for the sun, I would say,
right.
I don't think there's much more we can learn from measuring the magnetic field. What we need to do is measure what the flows look like in the interior of the sun. And of course, we have some idea from helioseismology, and we know something about the differential rotation in the star, in the sun, but we don't know very much about the meridional flow, or as much, and that's a much harder observation to make. So I would say we're going to learn more from observing the flows than from observing the fields.
Okay.
However, when people want to send up satellites to look at the sun, they always justify it by saying, we're going to measure the magnetic fields and it's going to give us some idea as to what the dynamo is going to do. But and who am I to, if they want to throw some money my way to do dynamo theory, that's absolutely fine. So this is not still being recorded, is it? Yeah.
Yes, it is.
It is. Okay. What was it? Pat said you have to cut that bit out. Yeah.
It won't be held against you.
Okay. I doubt anybody from the space agencies is going to look at this talk anyway. So.
Sadly, you're right.
Well, I think we're done. I don't see other questions. Are there a few more points which would like to raise? No. Okay, so I think we can thank you again, Steve, for this the entertaining talk and enlightening discussion. Thanks a lot.
Thank you. Oh, thanks everybody for staying to the end. Thanks everybody.
Thanks, Steve.
Bye. Bye, Graham. Bye, everybody.
Bye.